Here's another really useful application of de Moivre's theorem. This relies on the, the expansion here of de Moivre's theorem. So this is just a complex number with a size of 1 and a power of n. So de Moivre's theorem says that we multiply the angles, so we get n times theta for each of the angles, and we do the size to the power of n, so 1 to the power of n is still 1, so we have 1's coming out the front. Okay, and what we're going to do is we're going to effectively expand this bracket out by using the binomial theorem, and then collect the terms, which means that we'll have some real component plus j times the imaginary component. And if we're trying to find a cosine, then the cosine is going to match the real part, and if we try to muck around with the sines, then the sines will match the bit which is imaginary. Okay, so it's quite a useful trick, this matching real parts and matching imaginary parts for them to be equal. So let's have a go with trying to find cos of 3 theta. So we're going to start with cos of 3 theta. Cos of 3 theta. Okay, and according to the formula we're looking about here, the cosine is the real part, so we're only going to be interested in the real part of this expansion. Cos theta plus j sine theta cubed in this case. Okay, so we're looking for the real part, and if we expand this thing out, we get cos cubed theta plus 3 cos squared theta j sine theta plus 3 cos theta j squared sine squared theta plus j cubed sine cubed theta. If you're not quite sure how I did that, then you need to have a look at something called the binomial theorem, which you should have seen at some stage before you got here. So the binomial theorem will explain what I just did there. Excuse me. Now we're only after the real parts, so any parts which are imaginary we can do away with. So that's a real part. This has got a j in it, so that's imaginary. This has got a j squared, but j squared is equal to -1, so that's going to come back to being real, whereas j cubed is imaginary because it's j times j squared. J squared is -1, so it's negative j, so that bit's imaginary as well, so we're not interested in that portion. So the only thing we're left with is that cos 3 theta equals cos cubed theta, and j squared is negative, so it's going to be minus 3 cos theta sine theta. Okay, and that's now got an expression for cos 3 theta in terms of cos thetas and sine thetas. Okay, so that's part A done. Part B, if we want this in terms of cos theta only, then somewhere along the line I've got to get rid of the sine, which gives me a mistake I've made, haven't I? That should be sine squared. Sine squared. Okay, and there's a relationship which you should have seen somewhere in the past, which tells you that cos squared theta plus sine squared theta equals 1. So if I rearrange that, sine squared theta is 1 minus cos squared theta. And I can just substitute that into here. So cos 3 theta is cos cubed theta minus 3 lots of cos theta times 1 minus cos squared theta. So I can expand some brackets out here. This here will give me plus 3 cos cubed, and that cos cubed will give me 4 cos cubed, and then minus this term here, which is just 3 cos theta. So I now have cos 3 theta just in terms of cos thetas.